back, students. Welcome to Priya's Lifescience Academy. Today I'll continue with another ecology lecture which is about geometric growth. I teach you about exponential growth, logistic growth. Now today we will learn about geometric growth. And what's the difference between geometric growth and exponential growth? Although they both look like same, but there's a difference between them. So we will deal with that today. This lecture will be beneficial for those who are preparing for csirnet, Life Science, ICMR, NEET, and also those who are in bachelor's degree and in master's degree, and also for upsc ecology students. Okay, so pay attention and listen carefully. So what is geometric growth? In ecology, geometric growth refers to a pattern of population increase where the size of the population multiplies by a constant factor. This is very much important. It multiplies by a constant factor in each discrete time period. There is a specific time period upon which the population will multiply its number. This type of growth is often observed in organisms that reproduce in non-overlapping generations. Okay, there are non-overlapping generation, no overlapping generation present. And it happens in annual plants, some insects, where resources are abundant and environmental conditions are ideal. Much similar like exponential growth, where you have seen that where resources were unlimited and the environmental conditions were very good, very ideal. Such as the case in geometric growth, but what's the difference? The difference is that they will multiply it in discrete time period and it is multiplied by a constant factor. We will understand these terms much clearly as we go through the full lecture. Now, what are the key features? Number one, discrete growth. What does that mean? Geometric growth occurs in distinct time steps. That is yearly, it can be yearly, it can be seasonally. Like you know, some of the plants or animals, they only give birth seasonally or yearly, with each generation multiplying by the previous generation's population size by a constant factor. Okay, that's the main point of geometric growth. And the curve is J-shaped curve, much similar like exponential growth curve. You know that in exponential growth curve, the curve was J-shaped, and this is the same for this case. When graphed, geometric growth produces a J-shaped curve indicating an accelerating rate of population increase over time, assuming unlimited resources. It should be J-shaped curve because as resources are unlimited, population will tend to increase abundantly. Now, in ecological context, what are the main features of this geometric growth? Ideal conditions needs to be present. Geometric growth assumes no limiting factors, example food, space, predation. Like there's a lot of food, lot of space, no predation are affecting the population. In reality, most populations eventually face limitations leading to slower growth. As I told you earlier also that for exponential growth, the situation is very unreal because there should always be limitations in the environment. Now, what's the difference between exponential growth and geometric growth? While exponential growth often describes continuous growth modeled with differential equations, I told you d and dt equal to r, and that was the differential equation. And what's the difference? Look, it describes the continuous growth. The growth is very continuous. Geometric growth specifically refers to a population that reproduce in discrete time intervals. That means like it should be seasonally or annually. There should be a discrete time intervals between their generation. Okay, but in exponential growth, the growth is very continuous and there should be overlapping generations. Okay, for exponential growth. But for geometric growth, there should be no overlapping generation present. And the case is that transition to logistic growth. In natural settings, geometric growth is typically an early phase of population expansion. Okay, as the population grows, resource limitations usually setting, leading to a transition to a logistic growth. Yes, because at the initial case, there will be a lot of resources, so population will grow very nicely, but at time pass, there will be scarcity of the resource, so the population growth will be slowed down, where the growth rate slows and the population stabilizes at the carrying capacity. Okay, so that's the thing, and I hope you also remember what is carrying capacity. If not, then go to the previous video and watch it very nicely. Now we will understand that Geometric growth describes population growth for periodic breeders. I told you, like those who breed seasonally or annually. The equation of the geometric growth can be understood very nicely by the R0, capital R0, which is net reproductive rate. I hope you remember what is net reproductive rate, and if you know the net reproductive rate, you can easily understand population growth by using this R0, capital R0. For example, a butterfly breeds once a year, then we can understand the growth of the butterfly by knowing the population size at time t by using the equation, which is nt plus 1 is equal to R0 into nt. Okay, how? Because here you can see that nt plus 1 is the population size of females at generation t plus 1, where nt is the population size. You know that nt is the population size at generation t, and nt plus 1 is the population size at nt plus 1, that means at next generation. And R0 is the net productive rate, or the number of females produced per female per generation. So if R0 equal to 1.5, you know, and NT is 100, like the 100 females, 100 individuals are available at present, and you can easily take out NT plus 1, that is 1.5 into 100, that is R0 into NT, that is 150. So at first generation you can find out the population growth by just multiplying the net reproductive rate with the present population size. Okay, by this you can also take out the second generation nt plus 2, like 150, because the present population size is 150 now, 150 into R0, which is 1.5. But similarly you can take out the population growth at several generations. So by using the capital R0, net reproductive rate, you can take out the population growth for geometric breeders or for periodic breeders. Okay, now you can rewrite the equation more easily, that is nt is equal to n0 r0 t, where t is the number of generation and n0 is the number of females currently in the population, and R0, you know, R0 is the net productive rate. So if your N0 is 100, if 100 females are present at present, and if R0 is equal to 1.5 and T is equal to 5, or after 5th generation, T is 5, that is after 5th generation, then what you can get? You can get NT is equal to N0 into R0 to the power T. You will get this. Look, similar results. NT plus 5, 759.375, similar result. So this was the old equation. Now this equation is the new equation, more easily written. So NT equal to N0 R0 to the power T. So by using the net reproductive rate, you can easily take out population growth by this way. And I must say that no butterflies will be born in a fraction, so it should be 759, not 760. Okay. So I hope you understood how net reproductive rate is useful for taking out population growth for periodic breeders in case of geometric growth. Okay. So by this equation, you can take out population growth by using a specific time interval. So the time interval used here 5 generations. So after 5 generations, how many individuals will be left? So this is the true example of this. So by this example, so by this equation, you can take out the population growth after generation after generation. And so you know, when R0 is less than 1, the population eventually declines to extinction. I told you before, because while net reproductive rate is very much important, when it is less than 1, population will go extinct. When R0 is equal to 1, the population size remains constant. Okay, and when R0 is greater than 1, the population increases. You know this very clearly. When R0 is equal to 1, the population is at equilibrium, where no changes in population density occur. Even if R0 is only fractionally above 1, population increases is rapid. Okay, like here you can see in figure 8, and a characteristic J-shaped curve results. We refer to this characteristic curve as geometric growth. Here you can see the geometric growth, the J-shaped curve. Here R0 is 1.05, R0 is 1.10, R0 is 1.51, and here R0 is 1.32. 20. You can see by increasing the value of R0, the growth of the population increases abundantly. Okay, and it gives us a J-shaped curve. So for exponential growth and also for geometric growth, you get a J-shaped curve. Okay. Now, how do field data fit this model growth? Initially, in a new and expanding population where resources are not limited, geometric growth is often observed. I told you that resources should not be limited. Resources should be abundant in order to happen geometric growth. Because of the effort involved, now listen to this very carefully. Because of the effort involved in calculating the R0, which is net reproductive rate, ecologists sometimes use a shortcut to predict the population growth. So what is it? Imagine a bird species that breeds annually. To measure population growth, ecologists count the number of birds in the population. So let's say N0 is 100. So first of all, for example, at present you count the number of birds in a population 100. Okay. Next year, ecologists count 110 birds in the same population. So you are observing the population and you counted 110 birds in the next year. So N1 equal to 110. So first our N0 was 100, then N1 was, so in the next generation N1 was 110. Okay, so the finite rate of increase lambda is the ratio of the population size from one year to the next is calculated as. So here we can calculate the lambda, which is N1 by N0. And what is our N1? Our N1 is 110 and N0 is 100. So we can take out the rate of increase, finite rate of increase by doing this, which is 1.10. Now, if we take out the lambda, the rate of finite increase, we need not to take out the net reproductive rate, capital R0. So here, now the equation changes. Lambda is often given as the percent annual growth at t, and t is the number of years. So here it is number of years. Okay. Let's consider a population of birds growing at a rate of 5% per year. And after 5 years, how many birds would be there? So for the butterfly population growth example we talked about earlier, and we wrote nt equal to n0 r to the power t. This was the old equation, that nt equal to n0 r0 to the power t. But what's the new equation? The new equation is nt is equal to n0 lambda t. So old equation was nt equal to n0 r0 t, but the new equation is nt is equal to, the new equation is n0 lambda t. Very easily you can take this out because lambda is very easy to take out. If you know the number of population in generation 1 and you know the number of population in generation 2, you can easily take out the lambda. So the question was that at present, for example, let's consider a bird population is growing a rate of 5% per year. So per year it is increasing at a rate of 5%. So after 5 years, how many birds would be there? So what will be it? So our initial population is N0 is 100. You know, N0 is 100. And you also know that it increases 5% per year. So if at year 1 it is 100, so year 2 it will be 5%. 5% will be 105. So you have to now take out lambda. Lambda is equal to, you know, n1 by n0. So 105 divided by 100, which gives us 1.05. So you have to put this 1.05 into here. So 100 into lambda is 1.05 and this t is 5. So to the power 5, I'm writing here because no space. So to the power 5. So what we'll get, 100 into 1.05 to the power 5, you will get 127.6. So after 5th year, you will get this number of births. So it should be in the, it should not be in fraction, it should be in full number. So 128 births after the end of fifth year. So by this way you can take out the number of births year after year. So by using the previous example, which is nt equal to n0 r0t, you could take out the population number or the growth in generation interval. So one generation after generation, and it was tough to take out the net reproductive rate. But by using this equation, if you use lambda, it will give you the finite rate of increase by just dividing the number of individuals in the next year divided by number of individuals in the previous year. So by this example you can take out, you had the initial birth number, which is 100, and you knew that in each year birth grows at 5% per year. So you know if the initial birth is 100, in the next year the birth number will be 105. So 105 divided by 100, you took out the lambda. Now just multiply it with 100 and to the power 5. So after 5th generation you will get this number of births. So, and this equation is applicable to take out the population growth after year. But previous equation, that is nt equal to n0 r0 to the power t, this was for taking out population growth generation after generation. Okay, so I hope you understood how geometric growth is regulated and how will you take out the population growth in case of periodic breeders by using this equation. Okay, nt is equal to n0 lambda to the power t. Now let's move into the difference between the r0 and lambda. R0 represents the net reproductive rate per generation. I told you, per generation. And lambda represents the finite rate of population change over some time interval, often a year. I told you lambda for year-wise population growth. Where species are annual breeders that live 1 year, such as annual plants, R0 is equal to 1. So when will you use R0 formula and when will you use lambda formula? You have to think that if you are asked about the generation, that after this generation how many individuals will be there, you will use the R0 formula. And if you are asked about the population after year, so you will use the lambda. Okay, that's the basic thing. And population grow when R0 or lambda is greater than 1. You know, both R0 and lambda are very important parameter. So if they are greater than 1, population grow, and population decline when R0 lambda is less than 1, and are at equilibrium when R0 lambda is equal to 1. Okay. Now the difference between geometric and exponential growth, again, for time scale, geometric growth, discrete time. This model assumes that the reproduction occurs at specific intervals, I told you, annually or seasonally, and that generations do not overlap, I told you before. For exponential growth, it is a continuous time. The model assumes that production happens continuously over time and the population increases at every moment and the growth rate is constant at each instant. For geometric growth, commonly applies to species where non-overlapping generations like annual plants, some insects, where reproduction happens in bursts. It follows J-shaped curve. And for exponential growth, often used when populations have overlapping generation because they are reproducing just constantly. Many vertebrates, bacteria in continuous culture, the growth is smooth and continuous, producing a J-shaped curve that also shows rapid increase under ideal conditions. Okay. Now the difference between R0 and R, which one is net reproductive rate and one is small r, which is the intrinsic rate of increase. How the per capita rate of increase, small r, related to net reproductive rate? One is for geometric growth. This is for geometric growth, this is for exponential growth. The two quantities are very similar. Capital R0 reflects a generational growth rate. Okay, it's a generational growth rate, while small r denotes an instantaneous rate. Okay, this is the main difference between them. The capital R is the generational growth for generational growth, and small r is the intrinsic rate of increase. And you know, when small r equal to 0, population remains constant. When r is greater than 0, population increases, and when r is equal to 0, the population is referred to as being at equilibrium. If you put R0, growth of the population, along with time, you will get a J-shaped curve, and that's known as exponential growth. Now, we refer to this type of population growth, exponential growth, where you use the small r, that intrinsic rate of increase. Note that both exponential growth and geometric growth give very similar J-shaped growth curves. Okay, you can see here both capital R and small r gives us J-shaped curve, but identical values of r, small r and capital R, give very similarly shaped growth curves, but because of the compound nature of exponential growth, as in exponential growth, organisms are multiplying constantly. The rate of increase is slightly greater for exponential growth than geometric growth for identical values of small r and capital R0. If you put in the graph for identical values of small r and the capital R0, you could see that the small r, the graph is slightly higher for small r, as because for exponential growth the organisms are multiplying continuously, so for exponential growth the growth will be higher for organisms. Okay, and summary: for geometric growth, discrete time steps, because you have a discrete time interval used for populations that reproduce in non-overlapping generations, uses the multiplication factor lambda, I told you, finite rate of increase applied at each step. And for exponential growth, continuous time model used for populations with overlapping generations, described by a constant instantaneous growth, that is small r. Both models are idealized representations that assume unlimited resources. I told you both are for unlimited resources, and now you can understand the difference between them. In natural environments, factors like resource limitation eventually slow down their growth. Of course, if they are growing smoothly, but when resources are limited, their growth will be limited. Thank you, students, for listening. And as I always say, fight for your dreams and your dreams will fight for you. Thank you.